like all the rest of my hard drive space, so it may be going kind of slow.
WinDirStat. WinDirStat, my favorite program. It shows all of the WinDirStat.
Perfect. I'll get it. Okay. All right. So the complex power, really everything else comes from that, and knowing the relationship between the complex power and the real power and the reactive power. So if you go ahead a couple pages and look at the essentials, this power triangle kind of sums it all up, where you see that S is the hypotenuse of a right triangle. So S equals the square root of P squared plus Q squared, or P is the real power and Q is the reactive power. You can also see that angle phi there. That's the angle that gets you the power factor. And so the cosine of phi cosine is adjacent over hypotenuse is P over S. And so everything else kind of comes from knowing that relationship and knowing that the complex power is the real power plus J times the reactive power. And then knowing that the complex power is 1/2 times the peak voltage and the peak current, or the RMS voltage times the RMS current. Yes?
I actually got a question about that. So
Yes.
when you say the peak voltage, you mean the magnitude of that given you mean the magnitude of the V?
Yeah, so let's talk about that. So let's say I have a sinusoid right here. So this is V equals 5, that's 5 cosine omega t minus pi over 2. Okay, so what is the maximum voltage?
5.
What is the amplitude of that voltage?
5.
What is the magnitude of that voltage?
5.
They're all the same.
Okay.
Just like the one time.
They're all the same.
Got it. Then
Yep. So, and so yes. So, answer to your question, peak, yes, it is the magnitude of the phasor, because when we write this as a phasor, we write this as 5 angle negative pi over, or negative 90 degrees. Yeah.
In the power equations, isn't it the conjugate?
It is. Thank you so much.
For
Yeah, the current is the conjugate. That is very important. The current is the conjugate. For those of you who are hearing that term for the first time, why haven't you been coming to my sessions? And that's all I'm going to say about that. No, I lied. Okay, I will tell you. So what the conjugate means is if the current is 5 angle 30 degrees, then the conjugate is 5 angle negative 30 degrees. Or if you have this as in
rectangular form.
that kind of form, so if I had I equals 3 plus J4, the conjugate, I conjugate, would be 3 minus J4. And as long as we're talking about magnitudes, we know that the magnitude of I is the square root of a squared plus b squared. Well, that also equals the square root of I times I conjugate. That's actually the definition of magnitude, is the complex number times its conjugate, and then you take the square root. All right. Now, okay, yes.
I'm so sorry, but for the RMS, it's also its absolute value, right? Or no, not necessarily. We still need to put its phasor.
RMS is, you're always, phasors are always going to have a positive value. So when you're saying absolute value, are you talking about the magnitude of a complex number or the absolute value of a real number?
Oh, I'm sorry, I meant the magnitude.
So,
So like,
Yes, those are magnitudes.
oh
Yes.
no, I'm asking like whenever you plug in the formula, the complex power formula, do you?
Oh, no, those, okay, yeah, okay, so I see the question. All right, yeah, so let me explain that. You will see that I almost always use the complex forms because I like complex numbers. I'm a complex person. And so I will usually have V equals, S equals 1/2 V I conjugate, and I'm going to use the complex values because it doesn't really even make sense to talk about the conjugate of a magnitude because that's talking about the imaginary part. So these are not magnitudes. These are complex numbers with an imaginary part and an angle. But it is also true, anything where you're using the complex value, if they're all multiplied, remember when you multiply complex numbers, if I write them as phasors, when you multiply two phasors, if I have A angle theta times B angle phi, then when I multiply those, I get AB angle theta plus phi. I would add together those angles. So what is the magnitude, if I take the magnitude of A angle theta, and I multiply that times the magnitude of B angle phi, the magnitude is just the A, and the magnitude over here is just the B, I get AB. And so I get the magnitude. So whenever you have a formula that has the complex part, if you just use just the magnitudes all the way across, you're still going to have a true formula. So it is still true that apparent power, not just the magnitude of it, equals 1/2 the magnitude of the voltage times the magnitude of the current. That is still also true.
Oh, okay.
Okay, so where you start getting iffy as to like what part do I use is when you start talking about parts that are strictly the real parts or strictly the imaginary parts, because then that's already breaking your complex number up, which is why I tend to not use those formulas because I can't really remember how they go. So like for instance, if you look at the real power, it's defined here, the real average power is defined as the real part of the complex power. That's the way I always do it. I find the complex power and then I take the real part. But it also equals V squared R, those are just magnitudes, over the magnitude of the impedance squared. That is also true, and it comes from how you would yeah, and so it all works out. But when you start looking at these other formulas on this page, if they're in bold, it means the complex number. If they're not in bold, it means the magnitude. But on these formulas right here, it says like absolute value of z squared. That you can just take the magnitude and square it. But it does mean that the magnitude of z. But yeah.
Yeah, that explains my confusion.
Yeah.
So it's kind of like where in here in the formula says magnitude, but I see what you mean. Non-bolded are the magnitude.
Non-bolded are the magnitudes, bolded are the complex numbers.
Okay.
Yep. Okay, so moving along from here. So the other things that are essential to know have to do with the power factor, because we know that the cosine of the angle, the impedance angle, equals the power factor. But if you're just given the power factor, then phi equals the inverse cosine of the power factor. Well, the problem with that is, if you remember, if I take this angle and find its cosine, or I take this angle and find its cosine, they both have the same cosine because the cosine is the x value. The calculator is only going to give you the positive value. So if I give you that the power factor, if I say the power factor is 0.95, and I ask you for the angle of the impedance, you would say, wait a minute, I can't quite do that. I need more information. Because if you take the inverse cosine of 0.95, you might have the right answer. So inverse cosine 0.95 gives me 18 degrees. So I get 18.2 degrees, but I really only know if that's the angle when I give you the other information about whether it's leading or lagging. So if it's leading, then you're going to use the negative value, and if it's lagging, you're going to use the positive value. So if I said power factor is 0.95 leading, then you would take the inverse cosine and then you just slap a minus in front of it. Okay, so that's what you need to know. And then this chart tells you a little bit more about what these things are. So if it's purely resistive, then that means that your power factor is 1. It means that I is in phase with V, and it means the angle of your impedance is 0. So that means all the imaginary parts have canceled each other out. That's purely resistive. So whenever you have a question that asks for something about would make current in phase with voltage, or you're looking for maximum power transfer, or you're looking for make impedance entirely real, all of these things are saying the same thing. They're all saying that you need to get the imaginary part of the impedance equal to 0. So depending on what the question is, you might have some parts of the circuit, and then you have to say, well, what's this other part of the circuit that would do one of these things? And so you figure out the equivalent impedance of the rest of the circuit, and then you figure out, well, what imaginary part would I throw in there to make this equal to 0? You set the imaginary part equal to 0. For maximum power transfer, you find out the equivalent impedance of the rest of the circuit, and then you make your, you add to it a network or a load that is the conjugate of the rest of the circuit. Because when you add a conjugate to the number, that makes the imaginary parts go away. So you have this maximum power transfer is not exactly the same as the rest. These two just mean you need to make the imaginary part 0. Maximum power transfer means you have your load, Z load, equals Z equivalent conjugate. It does mean that your entire impedance is going to have a 0 imaginary part, but it also has to have the same magnitude. So that does make it a little bit different. And then you have leading and lagging. So it's called leading when the angle is negative, and that's when you have a capacitive network. It just means you are heavier on capacitors than inductors. Lagging, your angles will be positive, and where those come from is if you were to graph the current, it says I lags V. That just means V arrives to a certain place before I does. I is behind V, or V is behind, yeah. All right, and then some of these are the same formulas as above. I think they are almost all the same as above, but I just had them on a different worksheet, so I cut and pasted them again, except for maximum power is right here. I don't think that one's up there. I tend, if you were here yesterday, I tend not to use that one. I tend to find out what impedance I would need, and then just find out what the power is from that impedance. But you can also use this formula if you need to. And if you do, notice it's asking for the resistance of the load, and the V, I believe we discussed yesterday, is supposed to be V Thevenin. But I tend not to use that formula. then we also have, and I don't think I wrote these up here separately, I have
I
that,
have a question.
yes,
What is the right side of the ZS with the conjugate? What is that?
For maximum
The
power.
one above the maximum power transfer.
oh, Z
Uh,
source,
Z source. Okay.
Z source conjugate, yeah. So that says ZL equals Z source conjugate. It just means everything except the load. And so in the
Okay, thank you.
in the power formula, it says V source, and that would be the same as V Thevenin. I also have here, it's not like really that conspicuous, the units for the different kinds of power. That real power is watts, complex power is volt amps, and reactive power is volt amps reactive. The one time that I say, yeah, just plug into a formula, because in general, I'm not a big fan of plugging into formulas because it might mean that you don't really know what you're talking about. You're just using a formula. But for finding the shunt capacitor, it really is very convenient to use this formula. And so when you are asked to find a shunt capacitor to change the power factor, this formula will be come in handy. And so you can get the value of the capacitance. You will have what you're doing with a shunt capacitor is, if you think about our power, I'll bring it back. If you think about our power triangle, where we have our real power and our reactive power and our apparent power, you produce this apparent power, this S. The only thing you can get any work out of is the real power. And so the reactive power is not doing any work, but you have to produce it. And so if you want to maximize your effort, you would like to keep the same real power but reduce the amount of reactive power. And so if you can reduce the reactive power while keeping the real power the same, so here's Q, here's P, the real power stays the same, you also will reduce the amount of S, of apparent power, that you have to produce. And the way you would do that would be, because in most real situations, it's not that you have a capacitive load, you end up having an inductive load. That's just what happens with real motors and things like that. And so you have an inductive load, and so your reactive power is a positive Q. And so to bring it down, you would add a capacitor, because that brings in the negative power. And when you bring in that capacitor, that shrinks the Q, it shrinks your reactive power, and then, but it keeps the real power the same. And so in this formula, it was telling you Q old minus Q new, so you would figure out what those are, divided by omega, that's the frequency, and VRMS squared. And Q equals the power times the tangent of the inverse power factor, the inverse cosine of the power factor. I always find this formula kind of funny, because really, if you have P and the angle, you can figure out what Q is, or if you have P and Q, I usually don't just like plug into that formula. I usually just draw a triangle, because it's what it is. It's P and Q. So you would take the inverse cosine of P to get phi, and then you take the tangent of it, which is Q over P, and then you multiply by P to get rid of the P. And I say just find Q. I mean, if you have all that information anyway, just draw a triangle and find Q. Oh, it looks like I liked this formula so much I put it on here twice. Yes.
For the shunt capacitor formula, would the VRMS, would that be the voltage at the load, or?
The VRMS is the voltage of the load, yes. Yes. I will double check on that, and just in case that's not right and I don't do a problem with it, I'll send out an email if I'm wrong on that, but I think it has to be. Okay. Again, everything here is also a repeat of stuff that I have earlier, just in a different format. I kind of like this format, this right here, to kind of sums up all the power factor stuff. in a nice condensed sort of way. Okay, something else you will want to know that you'll want to have on your formula sheet, so this is a formula sheet thing, is for most of the Bode plot stuff, it's all the same. You have factors that look like 1 plus omega over omega c. All of your factors are going to look like that, and this c is your corner frequency or cutoff frequency, and that's what you're going to use. But if you have a quadratic factor, it looks a little different. So if you have a quadratic factor, you have to get it to look like this form in order to get the omega c, and to get the damping factor is this zeta right there. So if I had, for instance, the following quadratic, so let me see if I can get one.
Is that the problem that we were looking at? Oh, you're right.
Okay, so let's say this is my quadratic factor. So you have that quadratic factor. I don't have to factor anything out because my constant term is already 1. But before I can figure out what the corner frequency is, I have to rewrite the squared term as plus j omega over 10 squared. So it turned into a plus because j squared makes it negative. I've got the omega squared, and then the 10 is the square root of 100. So that tells me that omega c is 10. And from that, I can find the damping factor because I know the damping factor comes from J2 zeta omega over omega c. So J2 zeta omega over omega c is supposed to be my linear term. And in mine, that equals 5j omega. And so to get the damping factor from there, I would say, well, I found omega c, that's 10. So J2 zeta omega over 10 equals 5j omega. The j's will always cancel, the omegas will always cancel, and then I have zeta 2 over 10 equals 5, or zeta over 5 equals 5, or zeta equals 25, which is not really, I don't think that's reasonable, but it is the answer I got. So that would be the damping factor. And what that has to do with is when you have a circuit that has an oscillatory response, it has to do with how quickly it reaches its asymptotic value. And yes. Okay, and then I did a little work just on the off chance that he asked some questions about different kind of filters. He hasn't done that in recent years, but he has in the past. He did on my test when I took this. He said, "What kind of filter is this?" And at the time I was like, "A nice one." And so your choices are high pass, low pass, band pass, or band reject. And he's not going to give you band reject. And the way you tell what kind of filter you have is as follows. So if you have just RL, so you've got your voltage source, and you've got a resistor, and you've got an inductor, And you see, that's all you have. So this is going to be high pass or low pass depending on whether the load is in parallel with the resistor or if the load is in parallel with the inductor. So if the load is in parallel with the resistor, that's a low pass filter. And if the load is in parallel with the inductor, this doesn't make any sense if you're not here to hear what I'm saying, but if it's in, you don't really have two loads. If it's in parallel with the inductor, that's a high pass filter. And it works the opposite for an RC circuit. So for an RC circuit, if you put the load in parallel with the capacitor, then that's low pass, and in parallel with the resistor, that's high pass. Okay, so that's if you have just a resistor and an inductor, or just a resistor and a capacitor. And in those cases, also, your corner frequencies are easy because they're the inverse of the time constant. And so they're the omega C for an RL is R over L, and omega C for RC is 1 over RC. And omega C for RLC will be 1 over the square root of LC. That's the same as the resonant frequency, and so that's what you'd have. Now an RLC circuit is going to be a band pass, and you would have a band pass if you have if they're in series. So I have a resistor and inductor and a capacitor all in series. It's going to be band pass if my load is in parallel with the resistor. The other way I could set up an RLC circuit is to have my I don't think that's how I wanted to say it. Yeah, so this is what I mean by that. We have a resistor, and we have a capacitor, and we have an inductor, and we have our load. That's also a band pass. And then I have band reject on there, but I doubt you would have that.
Oh, for the band pass,
Yes.
it's in parallel with LNC. Because I think
Yes.
I'm just interpreting.
Yes,
what
you're,
it's
my
said
words.
wrong.
I wrote the words, so so if you're interpreting these words wrong, it's my writing that's not correct. So,
okay.
yeah, this is not. I meant. Did I not change it on here? I meant for it to be.
It's in parallel with the LNC.
I meant for these three things to be in parallel.
Okay. And then the R's in series. Okay.
And the resistors in series. Now that's not how it looks for a band reject. Or band reject, just in case you're curious, it's crazy. So the band reject has your capacitor and your inductor in parallel. And then you have your resistor, and that's where the load is with the resistor. That's band reject. And in case you don't know what we're talking about when we're saying these filters, that is something else that you do need to know, is what these filters are doing. It's why you do Bode plots, is to figure out the frequency response of your circuit. So what a filter does is it allows you to get just some part of the signal. It filters out parts of the signal. So the ideal low pass filter looks like this. This is frequency down here, that's angular frequency, and this is the magnitude of your transfer function, the magnitude of your response. What an ideal low pass says, up until my corner frequency, I get all of it, and after the corner frequency, I get none of it. So it's low pass. You let the low stuff through. High pass would be the opposite, and you would say, up until the corner frequency, I get none of it, and then after the corner frequency, I get all of it. Now, your actual filters are not these nice little step functions like that. They're not quite as good. The way it's actually defined is the corner frequency is the frequency at which h, so this is not equal, h of omega c equals h max over the square root of 2. That's the actual definition. And so it's when it has diminished to 1 over the square root of 2 of its original, or it has gotten to 1 over square root of 2 of the original, whether it's band pass or high pass or low pass. Band pass means that you have none of it, and then you have all of it, and then you have none of it again. You're getting some group with some set in the middle. Okay, and now I have Bode plots. I'll just talk about these when we do Bode plots. These are, your rules for them, unless you have a question on something that just like a factual question. And if not, I can take any questions on these kinds of concepts before I just jump into the problems. Yes.
For the decimal definition,
Yes.
shouldn't it be 20 log?
Oh, okay, kind of, sort of, not really, no. But, so what you're thinking of is, okay, so the definition of a decibel, the definition of a bell is actually, did you know there was a bell?
God, Alexander Graham.
So,
Yes.
oh, we were doing decibel conversions, and we were wondering why our results were like double his, but we were using 20 instead of 10 because 10 deci.
Well, no, that's not why.
Oh, no,
You'll
not
see
why?
why in a minute, yeah.
Oh, okay.
Okay, so a bell is a power ratio. It's not really a unit because it equals, the units are 1. So you're taking your power over some reference power. But for most of our needs, that number is not big enough. We need to scale it, and so instead of using the bell, we use a decibel, which is, a bell is a tenth of this, which means we take our number and we multiply it by 10. Just like if I say how many centimeters are in 1 meter, I have 100 of them. I multiply by 100, even though centi means 100th. And so we use decibels because multiplying by 10 makes it better. So that's the 10th part. But you're like, but wait a minute, I know I multiply by 20. Well, why is that? What is the definition of power in terms of voltage and resistance?
V squared divided by Z conjugates. I mean, the absolute value of V squared divided by Z conjugates.
Okay, so I'm just going to use R for fun. So I would have if I'm using voltages, which are a lot easier to measure than power, then I would have the voltage that I'm measuring over the resistance over some reference voltage over the same resistance, and then I'm going to take the log of that and multiply by 10, and that would be a decibel. But if I take the log, if I cancel out the R's, and I get V over V naught squared by the rules of logs, that 2 can come out in front, and I get 20 log V over V naught. And when we write our transfer functions, what are we having? What is our transfer function? What are we usually writing? We're usually writing V omega out over V omega in. These are voltages, not powers. And so, but since a decibel measures power, that's why we multiply by 20.
Oh wait, that's omega, right?
This is omega.
Oh, okay.
Yeah. So that's where the 20 comes from. So good catch and good question, and I'm really glad I got to answer that because I've been kind of working on figuring that out for, a while, so. Did that question, was that interesting to some of you at any rate? Yeah, okay, all right. You probably don't need to know that. What you need to know is how to make the Bodie plot. Okay, other questions? Yes.
A damping factor is only applicable to quadratic terms?
Damping factor is only applicable to quadratic terms, yes. And as he does not make you, and your book does not make you include that in your Bodie plot, there is a way to do it, to show it, but you don't have to do it. Yes.
The phasor
So
angle
what about
for
the
the
one in resin?
impedance, would it be the impedance angle also?
Yes, it is.
Okay, I'm just making sure, 'cause
Yes, it is. And so that is actually a good point, because let's say I'm working this power problem and I'm down, I just don't feel like I have enough information. And it's like, he didn't give me the power factor. How am I supposed to do this without the power factor? But you know what the impedance is? If your impedance is 5 minus J10, then you have your power factor. Because phi is the angle of the impedance, and the angle of the impedance is the inverse tangent of the imaginary part over the real part, or you just get your calculator to tell you what the angle is, and then your power factor is the cosine of that angle. So as long as you have the impedance, you've got what you need for the power factor. Okay, other questions? I have now, let's see, this is 1, 2, 3. This is my 4th semester doing Circuits 2. I've now reached my objective. When I started being the SI for Circuits 2, it was that I need to learn Circuits 2. Got there. Okay. All right. I'm going to stop this recording and start it uploading, and I'm going to switch to the other computer, and we're going to start working problems, if there are no other questions.